Okay, we're going to be doing LeetCode 278, first bad version. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails a quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions from 1 to n inclusive, and you want to find out the first bad one, which causes all the following ones to be bad. You are given an API with a Boolean return type called isBadVersion, which takes version. Version will be one of these, right? One of these integers, which returns whether version is bad or not. So it returns true if it's bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. So this screams modified binary search, right? Or what some call binary search variants, right? So let me show you why. Here, the algorithm is a binary search because if this is our array of the versions, starting from 1, 2, 3, 4, let's say 5, 6. Let's say our n is equal to 6 and it's a one based index, right? So that means that this is version 1, version 2, version 3, version 4, version 5, version 6, right? But since it's not an array, they're actual numbers, right? And we're going to access them using this, and we're going to use this. This is what we place into the isBad, this number right here, 1, is what we place into the isBadVersion API, right? And it will tell us if it's bad or not. So now we're going to assume that starting from, because they said that once there's a bad version, all the subsequent ones are bad, right? And they want us to find, grab this and put this here. They want us to find the first bad version, right? So let's say version 4 onwards is bad, right? So we don't know this, right? We're going to be making an API call using binary search where our I is here, our J is here. So that means every time we have to check whether a version, when we do a binary search and we get a midpoint, right? We check if it's not a bad version. Otherwise, our API call returns a false, right? If this is the case, then that means we extend our I up until, let's say our mid was at this location. Let's say our mid was at this location, right? Then that means that let's say our mid, we calculated our mid I plus J divided by 2, and our mid ended up at this location, right? At version 3. We checked this version and we discovered that it's not bad, because remember our bads for this example start from 4 onwards. So we increment our I past the mid to this position, right? And remember, by the time we finish the binary search, right? For binary search variant questions, once we get done with the binary search, our I will be at the first position where things start getting, where the rest of them fit the opposite condition. So let me write this code and then we can trace it. But it's not difficult at all, right? So as you can see here, you call version 3, 5, 4 is the first bad version. But the way we're going to do it is the binary search function will call based off mid, right? but at the end of the binary, when we exhaust the binary search, the I will go past J, right? And it will be at the first position of the bad versions. It's similar to ransom notation. I think it was ransom notation, a problem that we did earlier on. Oh, wait a second. I'd forgotten to take out the diagram. I meant these. But so let's do it. So I is equal to, we're going to have 2 pointers. So let's first write down our solution is a binary. I mean, you can obviously use linear search with this, but you may get a time limit exceeded or something like that, right? Because, okay, let's first do the linear search and see linear search operation, right? It will simply be for I in range 1 to n plus 1, right? Because we're trying to include the n, right? And we're trying to have a 1 base index. Then we'll say if is bad version and I, then we found our first bad version, right? Because it will return true, and this will be the first, right? But we're trying to minimize the number of API calls. That's why we're not going to use this linear search operation. We're going to cut the API calls by log n. So we simply return I, right? See? But we have a memory error, right? So there's not enough space because the API call for n was extremely large, right? So it's a runtime error. It's not a logical error, whatever. It's a runtime error. It's a memory exception error. So how do we minimize our API calls? We minimize them by using binary search variants or modified binary search. And the beauty to modified binary search is it helps us determine where the first value that, let me write the code and then you'll get it. So I is equal to 1, right? Because our versions start from version 1 to n. And then j will equal to n, right? Because n is included, right? So while I is less than or equal to j, we calculate our mid. So this will help us reduce the number of values we're looking at. So mid is equal to I plus, in brackets, j minus I, divided by 2. Then we check if our mid returns a false. So if is bad version at mid is equal to false, it means that we still haven't yet reached that point where the values are bad, right? Where our version is bad. So we increment our mid to +1, right? Mid +1. So let me show this in the diagram again. So what we've done, here, what we've done with this code, right, is if we have our versions 1, 2, 3, 4, 5, 6, and from 4 onwards, they're bad, we are saying that if we've calculated our mid and our mid is here, we want, and say our I was here, right? We want our I to move from the location where it's at, right, our mid is here. We want to discard all the values to the left. So we want our mid to come here. And we'll discard these values because we are not yet there. So let's say we calculate again, and then we discover that, you know what? Our mid is now going to come here. Then we check again. When we put this into his bad, when we put this into his bad version, it still doesn't give us the, if we put this mid into his bad version, it still returns false. Again, we push our mid +1, right? That's what we're trying to do with this code. Else, it will mean that the is bad version return true. And if it returns true, it means that we are, let me write it here. If our else is, it means is bad version returned at mid is equal to true. So it means we are in the section. It means, for example, if our 1, 2, 3, 4, 5, 6, and we know from 4 onwards, this is the bad section, right? This is the bad section, bad version section. It means that maybe our mid is here, right? So we want to discard all these others and move our J pointer, say our J pointer was here. We want to move our J pointer past the mid, right? So when we go back to the code, our J is equal to mid -1. So this modified binary search or binary search variants work by exhausting this whole thing. And then after it's all done, what will happen is, let me redo it here. 1, 2, 3, 4, 5, 6. This is our bad section. After the whole modified binary search is done, our I will be at the first position where because remember it terminates when I is less than J, right? So our I will be here and our J will actually be here, right? That's how it terminates. So we simply return I. So this may not make sense right now, but if you've been doing binary search variants, then let's see, you'll be able to do this. Let's see. Okay. So here we simply return I, right? Because as I showed you, the I will end up at the first, position of the bad versions after the binary search is exhausted, and J will end up at the last position of the good versions. So either return J +1 or I, right? So let's submit this code and see what happens. Voila, it works, right? Notice if I submitted J +1, it will also work, right? So now let's trace this code and see what's up, right? Just do a little trace. Let's look at what test case did they give. 5, and they start being bad from 4, right? Okay, so we're going to just do a trace of the code using this test case, right? Our n is 5 and the first bad case is at 4, right? So we'll delete this. We're going to have 1, 2, 3, 4, 5. These are our versions, right? These are our versions, product versions. Our I is at 1, our J is at N. Remember, our N is 5, right? We already know that our API call starts being bad from 4, right? We're just doing this for an example, right? So let's start from here. We've initialized the pointers. If you look on the diagram, you can see our I and J, right? Then we come down here, while I, let me write here I, and here J. Our I is 1, our J is 5. So we come down here, our mid is I plus J divided by 2. You can also write it like this. So 1 plus 5 divided by 2 gives us 3, right? So that means we look at this position as our mid, right? So is bad version at mid? Remember, we have this insight that it will start at 4. So this returns true, right? Is bad version at 3 will return false, sorry. It's not a bad version. So that means we want to discard all these, including the mid, right? So we execute this, mid plus 1. Our mid comes past, and now it's at 4, and we come back all the way up here in the code, right? So our I is now 4, our J is still 5. So we come down here, we calculate our mid. Our mid is 4 plus 5 divided by 2. 9 divided by 2 gives us 4, because we truncate, right? So our mid is now at 4, right? We do our API call. Our API call, if is bad version is equal to false, is not equal to false, right? Because, sorry, we know we had that insight that it's what? It's true. It returns true. So we come to our else condition. Is bad version mid is true, meaning we want to discard all these, including the mid for the J, right? So our J pointer comes here, right? So now our J pointer is at 3, our I is at 4, right? So we've executed this. So now we come back up here. While I is less than or equal to J, is I less than or equal to J here in that diagram? No. I is larger than J, so we break out. And once we break out, as you can see in the diagram, I is at the first position and J is at the last position, at which we did not have bad versions, right? So our answer is I, or it's J plus 1, which is also equal to 4, right? But for here, I would highly suggest that you use I. It will be easier to remember. So that is the solution to first bad version. And it's a binary search variant, right? Okay, and this is a log n solution. So thank you and bye.